Artificial gravity is the theoretical increase or decrease of apparent gravity via artificial means, particularly in space, but also on Earth. It can be practically achieved by the use of different forces, particularly the centripetal force and linear acceleration. The creation of artificial gravity is considered desirable for long-term space travel or habitation, for ease of mobility, for in-space fluid management, and to avoid the adverse long-term health effects of weightlessness. A number of methods for generating artificial gravity have been proposed for many years, as well as an even larger number of science fiction approaches using both real and fictitious forces. Practical outer space applications of artificial gravity for humans have not yet been built and flown, principally due to the large size of the spacecraft that would be required to allow centripetal acceleration rotating spacecraft. Requirement for gravity: without G-force, space adaptation syndrome occurs in some humans and animals. Many adaptations occur over a few days, but over a long period of time bone density decreases, and some of this decrease may be permanent. The minimum G-force required to avoid bone loss is not known. Nearly all current experiences with G-forces of 1 g or 0 g in orbit. There has not been sufficient time spent on the Moon to determine whether or not lunar gravity is sufficient. A limited amount of experimentation has been done by Dr. Alfred Smith, of the University of California, with chickens, since they are bipeds, and mice experiencing high G-force over long periods in large centrifuges on the Earth. Rats have been exposed to continuous artificial gravity of 1 g during Russian biosatellite missions lasting 2 weeks. The muscle and bone loss in these animals was found to be less than rats in 0 g. Astronauts were exposed to artificial gravity levels ranging from 0.2 to 1 g for a few minutes during several spaceflight missions, using linear sleds or rotating chairs. They did not perceive any changes in their spatial orientation when the G level was lower than 0.5 g at the inner ear level, where the sensory receptors for gravity perception are located. Methods for generating artificial gravity: gravity can be simulated in numerous ways. Rotation. A rotating spacecraft will produce the feeling of gravity on its inside hull. The rotation drives any object inside the spacecraft toward the hull, thereby giving the appearance of a gravitational pull directed outward. Often referred to as a centrifugal force, the pull is actually a manifestation of the objects inside the spacecraft attempting to travel in a straight line due to inertia. The spacecraft's hull provides the centripetal force required for the objects to travel in a circle. Thus, the gravity felt by the objects is simply the reaction force of the object on the hull reacting to the centripetal force of the hull on the object, in accordance with Newton's third law. From the point of view of people rotating with the habitat, artificial gravity by rotation behaves in some ways similarly to normal gravity but has the following effects: centrifugal force. Unlike real gravity which pulls towards a center, this pseudo-force that appears in rotating reference frames gives a rotational gravity that pushes away from the axis of rotation. Artificial gravity levels vary proportionately with the distance from the center of rotation. With a small radius of rotation, the amount of gravity felt at one's head would be significantly different from the amount felt at one's feet. This could make movement and changing body position awkward. In accordance with the physics involved, slower rotations or larger rotational radii would reduce or eliminate this problem. As per Newton's third law, the Coriolis effect gives an apparent force that acts on objects that move relative to a rotating reference frame. This apparent force acts at right angles to the motion and the rotation axis and tends to curve the motion in the opposite sense to the habitat spin. If an astronaut inside a rotating artificial gravity environment moves towards or away from the axis of rotation, he will feel a force pushing him towards or away from the direction of spin. These forces act on the inner ear and can cause dizziness, nausea and disorientation. Lengthening the period of rotation reduces the Coriolis force and its effects. It is generally believed that at 2 rpms or less, no adverse effects from the Coriolis forces will occur. At higher rates some people can become accustomed to it and some do not. But at rates above 7 rpms few if any can become accustomed. It is not yet known if very long exposures to high levels of Coriolis forces can increase the likelihood of becoming accustomed. The nausea-inducing effects of Coriolis forces can also be mitigated by restraining movement of the head. This form of artificial gravity gives additional system issues. Kinetic energy, spinning up parts or all of the habitat requires energy. This would require a propulsion system and propellant of some kind to spin up or a motor and counterweight of some kind to spin in the opposite direction. Extra strength is needed in the structure to keep it from flying apart due to the rotation. However, the amount of structure needed over and above that to hold a breathable atmosphere is relatively modest for most structures. If parts of the structure are intentionally not spinning, friction and similar torques will cause the rates of spin to converge, requiring motors and power to be used to compensate for the losses due to friction. A traversable interface between parts of the station spinning relative to each other requires large vacuum-tight axial seals. The engineering challenges of creating a rotating spacecraft are comparatively modest to any other proposed approach. Theoretical spacecraft designs using artificial gravity have a great number of variants with intrinsic problems and advantages. To reduce Coriolis forces to livable levels, a rate of spin of 2 rpms or less would be needed. To produce 1 g, the radius of rotation would have to be 224 am or greater, which would make for a very large spaceship. To reduce mass, the support along the diameter could consist of nothing but a cable connecting two sections of the spaceship, possibly a habitat module and a counterweight consisting of every other part of the spacecraft. It is not yet known if exposure to high gravity for short periods of time is as beneficial to health as continuous exposure to normal gravity. It is also not known how effective low levels of gravity would be to countering the adverse effects on health of weightlessness. Artificial gravity at 0.1 g would require a radius of only 22 am. Likewise, at a radius of 10 m, about 10 rpms would be required to produce Earth gravity, or 14 rpms to produce 2 g. If brief exposure to high gravity can negate the health effects of weightlessness, then a small centrifuge could be used as an exercise area. The Gemini 11 mission attempted to produce artificial gravity by rotating the capsule around the edge near target vehicle which it was attached to by a 36-meter tether. They were able to generate a small amount of artificial gravity, about 0.00015 g, by firing their side thrusters to slowly rotate the combined craft like a slow-motion pair of bowlers. The resultant force was too small to be felt by either astronaut, but objects were observed moving towards the floor of the capsule. The proposed Tempo 3 mission rotates two halves of a spacecraft connected by a tether to test the feasibility of simulating gravity on a manned mission to Mars. The Mars Gravity Biosatellite was a proposed mission meant to study the effect of artificial gravity on mammals. An artificial gravity field of 0.38 g was to be produced by rotation. 15 mice would have orbited Earth for 5 weeks and then land alive. However, the program was cancelled on June 24, 2009 due to lack of funding and shifting priorities at NASA. In amusement parks, pendulum rides and centrifuges provide rotational force. Roller coasters also do, whenever they go over dips, humps, or loops. When going over a hill, time in which zero or negative gravity is felt is called air time, which can be divided into floater air time, and ejector air time. Linear acceleration, even at a low level, can provide sufficient g-force to provide useful benefits. Any spacecraft could continuously accelerate in a straight line, forcing objects inside the spacecraft in the opposite direction of the direction of acceleration. Most chemical reaction rockets already accelerate at a sufficient rate to produce several times Earth's g-force but can only maintain these accelerations for several minutes because of a limited supply of fuel. A propulsion system with a very high specific impulse could accelerate more slowly, producing useful levels of artificial gravity for long periods of time. A variety of electric propulsion systems provide examples. Two examples of this long-duration, low-thrust, high-impulse propulsion that have either been practically used on spacecraft or are planned in for near-term in-space use are Hall effect thrusters and variable specific impulse magnetoplasma rockets. Both provide very high specific impulse but relatively low thrust, compared to the more typical chemical reaction rockets. They are thus ideally suited for long-duration firings which would provide limited amounts of, but long-term, milli-G levels of artificial gravity in spacecraft. Low impulse but long-term linear acceleration has been proposed for various interplanetary missions. For example, even heavy cargo payloads to Mars could be transported to Mars in 27 months and retain approximately 55% of the LEO vehicle mass upon arrival into a Mars orbit, providing a low gravity gradient to the spacecraft during the entire journey. Constant linear acceleration could theoretically provide relatively short flight times around the Solar System. If a propulsion technique able to support 1 g of acceleration continuously were available, a spaceship accelerating at 1 g would reach Mars within a few days. In a number of science fiction plots, acceleration is used to produce artificial gravity for interstellar spacecraft, propelled by as yet theoretical or hypothetical means. This effect of linear acceleration is very well understood, and is routinely used for zero-G cryogenic fluid management for post-launch in space firings of upper-stage rockets. Roller coasters, especially launched roller coasters or those that rely on electromagnetic propulsion, can provide linear acceleration gravity, and so can relatively high acceleration vehicles, such as sports cars. Linear acceleration can be used to provide airtime on roller coasters and other thrill rides, such as the Twilight Zone Tower of Terror. Magnetism. A similar effect to gravity has been created through diamagnetism. It requires magnets with extremely powerful magnetic fields. Such devices have been made that were able to levitate at most a small mouse and thus produced a 1 g field to cancel the Earth's. Sufficiently powerful magnets require either expensive cryogenics to keep them superconductive, or require several megawatts of power. With such extremely strong magnetic fields, safety for use with humans is unclear. In addition, it would involve avoiding any ferromagnetic or paramagnetic materials near the strong magnetic field required for diamagnetism to be evident. Facilities using diamagnetism may prove workable for laboratories simulating low-gravity conditions here on Earth. The mouse was levitated against Earth's gravity, creating a condition similar to microgravity. Lower forces may also be generated to simulate a condition similar to lunar or Martian gravity with small model organisms. Gravity generator gravitomagnetism. In science fiction, artificial gravity or paragravity is sometimes present in spacecraft that are neither rotating nor accelerating. At present, there is no confirmed technique that can simulate gravity other than actual mass or acceleration. There have been many claims over the years of such a device. Eugene Podkoltnov, a Russian engineer, has claimed since the early 1990s to have made such a device consisting of a spinning superconductor producing a powerful gravitomagnetic field, but there has been no verification or even negative results from third parties. In 2006, a research group funded by ESA claimed to have created a similar device that demonstrated positive results for the production of gravitomagnetism, although it produced only 100 millionths of Ag. String theory predicts that gravity and electromagnetism unify in hidden dimensions and that extremely short photons can enter those dimensions. Training for high or low gravitational environments, centrifuge. High-G training is done by aviators and astronauts who are subject to high levels of acceleration in large radius centrifuges. It is designed to prevent Ag-induced loss of consciousness, a situation when G-forces move the blood away from the brain to the extent that consciousness is lost. Incidents of acceleration-induced loss of consciousness have caused fatal accidents in aircraft capable of sustaining high G for considerable periods. Parabolic flight. Weightless Wonder is the nickname for the NASA aircraft that flies parabolic trajectories and briefly provides a nearly weightless environment in which to train astronauts, conduct research, and film motion pictures. The parabolic trajectory creates a vertical linear acceleration which matches that of gravity, giving 0 g for a short time, usually 20–30 seconds, followed by approximately 1.8 g for a similar period. The nickname Vomit Comet is also used to refer to motion sickness that is often experienced by the aircraft passengers during these parabolic trajectories. Such reduced gravity aircraft are nowadays operated by several organizations worldwide. Neutral buoyancy. A neutral buoyancy laboratory is an astronaut training facility, such as the Sonny Carter Training Facility at the NASA Johnson Space Center in Houston, Texas. The NBL is a large indoor pool of water, the largest in the world, in which astronauts may perform simulated EVA tasks in preparation for space missions. The NBL contains full-sized mock-ups of the Space Shuttle cargo bay, flight payloads, and the International Space Station. The principle of neutral buoyancy is used to simulate the weightless environment of space. The suited astronauts are lowered into the pool using an overhead crane, and their weight is adjusted by support divers so that they experience no buoyant force and no rotational moment about their center of mass. The suits worn in the NBL are down-rated from fully flight-rated EMU suits like those in use on the Space Shuttle and International Space Station. The NBL tank itself is 202 feet in length, 102 feet wide, and 40 feet 6 inches deep, and contains 6.2 million gallons of water. Divers breathe nitrox while working in the tank. Neutral buoyancy in a pool is not weightlessness, since the balance organs in the inner ear still sense the up-down direction of gravity. Also, there is a significant amount of drag presented by water. Generally, drag effects are minimized by doing tasks slowly in the water. Another difference between neutral buoyancy simulation in a pool and actual EVA during spaceflight is that the temperature of the pool and the lighting conditions are maintained constant. Proposals. There have been a number of proposals that have incorporated artificial gravity into their design. Discovery 2 was a 2005 vehicle proposal capable of delivering 172 T to Jupiter's orbit in only 118 days. A very small portion of the 1,690 T craft would incorporate a centrifuge where the crew would reside. Multi-mission space exploration vehicle. This 2011 NASA proposal for a long-duration crewed space transport vehicle includes a rotational artificial gravity space habitat intended to promote crew health for a crew of up to 6 persons on missions of up to 2 years duration. The partial G-torus ring centrifuge would utilize both standard metal frame and inflatable spacecraft structures and would provide 0.11 to 0.69 G if built with the 40 feet diameter option. ISS centrifuge demo, also proposed in 2011 as a demonstration project preparatory to the final design of the larger torus centrifuge space habitat for the multi-mission space exploration vehicle. The structure would have an outside diameter of 30 feet with a 30 inches ring interior cross-section diameter and would provide 0.08 to 0.51 G partial gravity. This test and evaluation centrifuge would have the capability to become a sleep module for ISS crew. Mars Direct, a plan for a manned-Mars mission created by NASA engineers Robert Zubrin and David Baker in 1990, later expanded upon in Zubrin's 1996 book The Case for Mars. The Mars Habitat Unit, which would carry astronauts to Mars to join the previously launched Earth return vehicle, would have had artificial gravity generated during flight by tying the spent upper stage of the booster to the habitat unit, and setting them both rotating about a common axis. Gen 1 Enterprise, an experienced engineer who goes by BTE Dan, created a website outlining in great detail how, with current technology, we could build the first generation of a full-sized spaceship Enterprise that could carry 1,000 people all over our solar system in reasonable amounts of time. The conceptual design is complete with a centrifugal gravity wheel to provide spacious, comfortable living spaces for the crew. See also, media related to artificial gravity at Wikimedia Commons, non-inertial reference frame, anti-gravity, artificial gravity in fiction, Coriolis effect, centrifuge accommodations module, fictitious force, rotating wheel space station, space habitat, Stanford Torus, references. External links, list of peer review papers on artificial gravity, Mars Gravity Experiment homepage, revolving artificial gravity calculator, overview of artificial gravity in sci-fi and space science, NASA's Java simulation of artificial gravity, variable gravity research facility, concept with tethered rotating satellites, perhaps a Bigelow expandable module and a spent upper stage as a counterweight.